Hello everyone, welcome to chapter 6. In this chapter, we are going to learn how astronomers use light and telescopes to understand the universe. So think about this for a second. When you look up at the night sky, what do you notice about the stars? They are tiny points of light, but each one carries a story about its distance, temperature, and composition. Now, before we jump in, ask yourself, why do you think telescopes are so important for astronomy? So, in this chapter, we will see how even invisible light reveals things our eyes alone cannot see. So, we will move from the basics of light to the incredible instruments astronomers built to study the universe. Some on Earth, some high above our atmosphere in space. Now, to guide our learning, let's first look at what you should be able to do by the end of this chapter. So, this will help you focus on the key ideas as we go. So, by the end of this chapter, you will be able to do three main things. First, you will understand the nature of light and how telescopes use it to study celestial objects. Think of light as the universe's messenger. Everything we know about distant light stars and galaxies comes from it. Next, you will be able to compare different types of telescopes, from small optical ones to massive space-based observatories like the James Webb Space Telescope. So, why do some need to be in space? Keep that connection in mind. And finally, you will learn about the instruments and techniques astronomers use to record and analyze light. It's not just looking through a telescope, it's capturing, measuring, and interpreting what the light tells us. So, as you move through the chapter, ask yourself, how does each new tool or technique give us a clearer picture of the universe? Alright, let's take a peek at the roadmap for this chapter. What topics we will cover and how the ideas build on each other. So here's how the chapter is structured. We start with radiation, information from space, which explains how light carries information from distant objects. So this sets the foundation for everything else. Then we dive into telescopes, learning the principle behind them and how they collect light. Next, we will look at the observatories on Earth, covering both optical and radio telescopes, and consider what advantages and challenges come with being on the ground. So, from there, we will explore airborne and space observatories. Why do astronomers sometimes need to go above the atmosphere? So, think about the limitations of looking through air and clouds and how space telescopes solve with those problems. And finally, we will examine astronomical instruments and techniques, the tools and methods astronomers use to extract as much information as possible from the light they collect. So, as you go through each section, try to connect it back to the learning objectives. How light is used, the power and limits of telescopes, and the techniques for studying what we see. So, by the end of this chapter, you will not only understand how telescopes work, but also why they are essential for unraveling the secrets of universe. So, keep your curiosity alive and remember, every piece of light carries a story waiting to be discovered. Alright, now first let's introduce how astronomers use light to study the universe. So, light is not just something we see. It's a messenger carrying information across space. And astronomers can tell a lot about a star, planet, or galaxy just by studying the light it emits. So today we will see how light behaves both as a wave and as a particle. Now, unlike the first astronomers who mapped constellations, modern astronomy relies on analyzing lights from objects millions or even billions of kilometers away. And by studying light, they figure out composition, temperature, movement, and even internal processes of celestial objects. So every photon that arrives at Earth is like a tiny package of data. The color, intensity, and energy of that light tells us about chemical elements in stars, how fast they are moving, and whether they are cooling or heating up. Now think of a rainbow. You see it because light waves bend and spread into different colors. But when light hits a camera sensor, it behaves as particles called photons, creating an image. So this dual nature is called wave-particle duality, and it's essential for understanding how telescopes and detectors work. So let's look at these two images. Notice the colors smoothly spread out in the rainbow. So this is a wave phenomenon, and each color corresponds to a slightly different wavelength, which we will discuss in a moment. Now in this camera capturing light, photons are absorbed by a detector, showing the particle nature of light. So modern instruments measure photons individually to collect data about distant objects. Now so far, we know light carries information and behaves in two ways. But how do we measure and quantify light? That's where wavelength, frequency, and energy come in. So let's look at that next. Now let's first explore how light behaves as a wave. Now two properties are crucial: wavelength lambda and frequency nu. And these properties are linked to the energy of photons, which are the particles of light. Therefore, understanding this relationship lets astronomers determine the physical conditions of stars and galaxies. So what is wavelength? Wavelength is like the distance between waves on the ocean. Shorter wavelengths mean waves are tightly packed, and longer wavelengths are more spread out. Next, frequency. So frequency is how fast the wave oscillates at a point. So high frequency means more peaks per second, and low frequency means fewer peaks. And if you multiply wavelength and frequency, then you get the speed of light, about 3 times 10 to the power 8 meters per second, which is a constant. So this relationship holds for all types of electromagnetic radiation, from radio waves to gamma rays. So anytime we know two of these quantities, we can calculate the third. Now imagine you know the frequency of a radio station. Could you calculate the wavelength? So that's exactly what astronomers do for all types of light. Now here's where the wave-particle duality comes in. Light doesn't just behave like a wave. It also behaves like a stream of particles called photons. And each photon carries energy, and that energy is inversely proportional to its wavelength lambda. So shorter wavelength photons like X-rays carry more energy. When lambda decrease, E increase, right? And longer wavelength photons like radio waves carry less energy. So think about it. A single photon of visible light carries far less energy than an X-ray photon. Yet both travel through space as light. So this is why astronomers need sensitive instruments to detect faint photons from distant stars. Sorry about the confusion. This equation should be E proportional to 1 over lambda. There is no equal sign, okay? It's just E proportional to 1 over lambda. Alright, now let's make this concrete with a practical exam, shall we? Okay, so let's practice with the radio station. So this will demonstrate how wavelength and frequency are related and how to use the formula lambda nu equals C in real situations. So now we are asked to calculate the wavelength of radio waves emitted by an FM station broadcasting at 89.5 megahertz. Now before I solve it, take a moment to think. Which formula might we use to connect wavelength and frequency? Now first let's identify the known values. The frequency of the radio station, it's the nu, it's given as 89 megahertz, right? That means 89 million hertz. That means 10 to the power 6, right? And the speed of light is always 3 times 10 to the power 8 meters per second. It's a constant like gravity. And now we want to find the wavelength of the wave, which is lambda. So what is the formula? The formula connecting wavelength and frequency is lambda nu equal to c. Lambda is the wavelength, nu is the frequency, and c is just the speed of light. So let's isolate the unknown parameter lambda. So lambda is just c over nu. Now we can substitute the numerical values to get the answer. So c is 3 times 10 to the power 8 and nu is just 89.5 times 10 to the power 6 hertz. Therefore, the answer is 3.35 meters. So we get the wavelength is about 3.35 meters. Now notice how the wave is much longer than the visible light, which is only a few hundred nanometers. So this shows the inverse relationship. Higher frequency, shorter wavelength, right? So this principle applies across the electromagnetic spectrum from radio waves to gamma rays. Alright, now that we have talked about wavelength, frequency and photons, let's zoom out and see the entire electromagnetic spectrum. So this spectrum shows all types of light from the longest radio waves to the shortest gamma rays. Now our eyes only detect a tiny slice called the visible light. But astronomers use instruments to detect light across the whole spectrum. Now at the long end are radio waves, which can be several meters to kilometers long. Next are microwaves, which you may know from your kitchen, right? And then infrared, which is associated with heat. So these are the gentle parts of the spectrum with low energy photons. So think about a microwave oven. It heats food by vibrating water molecules with microwave radiation. And astronomers use the same part of the spectrum to study cold gas and dust clouds in space. Interesting, right? Now what is this narrow band? So this narrow band is the light our eyes are tuned to. From red at 700 nanometers down to violet at 400 nanometers. So this is the rainbow. But see, it's just a tiny fraction of all the light out there. And at the short end, photons are extremely energetic. Ultraviolet light gives you sunburns, and X-ray come from hot gas around black holes. And gamma rays are produced in extreme events like supernova and neutron star collisions. So again, look at this figure. The white band shows the full spectrum and the tiny rainbow strip in the middle is just the visible light, the light we see. So notice how small it is compared to the whole scale. So most of the universe radiation is invisible to our eyes. Now our eyes are evolved to see visible light, right? Why is that? Because Earth's atmosphere happens to let it through. But astronomers know the universe glows in many other forms of light. So by detecting these other wavelengths, we can uncover hidden layers of the universe, like X-rays showing hot gas or radio waves revealing cold hydrogen clouds. Now imagine if humans could see infrared. Then we would see the heat radiating from people, animals and even our coffee cups. So how different would the night sky look? So now our atmosphere is like a natural filter. It only allows visible light and some radio waves through. And that's convenient because without visible light we couldn't see at all. And without radio waves we wouldn't have wireless communication. But most other radiation is blocked, and ozone in the atmosphere absorbs harmful ultraviolet rays, which protects life. and water vapor and carbon dioxide block infrared. So this is great for survival but not so great for astronomers who want to study those wavelengths. Now the next figure B shows which wavelengths get through. The colored strip at the bottom mark the transparent window, visible and some radio. All the blocked parts explain why astronomers launch telescopes into space to observe X-rays, gamma rays and infrared. So the electromagnetic spectrum is our full toolkit. Each part gives astronomers unique information from cold gas clouds seen in radio to black holes glowing in X-rays. So together, this spectrum is like a cosmic encyclopedia. Alright, now let's take the next step. How astronomers use this light to extract details about stars and galaxies. So we will connect wavelength and photon energy to the physical processes happening in distant objects. Alright, let's first ask, why is light so important to astronomers? Remember, we can't travel to stars or galaxies directly. Light is our messenger. So every photon that reaches us carries clues about where it came from. And by analyzing that light, astronomers can unlock the secrets of the universe. Now by splitting light into spectrum, astronomers see patterns of lines that act like fingerprints of elements. Hydrogen, helium, oxygen all leave unique marks. And this is how we know what stars and galaxies are made of without ever visiting them. So think, if you could only look at the glow from a candle, could you figure out what chemicals are burning? But astronomers do this all the time with starlight. And the color of light tells us the temperature. So blue stars are hotter than red stars. Just like metal glows red when heated, then white hot. So stars follow the same pattern. And light shifts in wavelength when objects move. If a star moves toward us, its light shifts slightly blue. And if it moves away from us, it shifts red. So this is called Doppler effect. And it is how we measure the speed of galaxies moving across the universe. So by observing changes in brightness, color and composition over time, astronomers track how stars age and galaxies evolve. So we say light provides the timeline of the cosmos. And the shorter wavelength waves like UV, X-ray and gamma photons carry a lot of energy. So they come from hot, violent places like the sun's corona, exploding stars or matter spiraling into black holes. And they can also be dangerous to life, which is why Earth's atmosphere blocks most of them. And the longer wavelengths like infrared and radio are gentler photons. They carry less energy. So infrared reveals cooler objects like planets, forming stars, and even the heat from your body. And the radio waves penetrate dust clouds, allowing us to see structures hidden from view in visible light. So this is why radio telescopes often reveal galaxies filled with gas and dust that look almost invisible to the naked eye. Now, unlike sound, which needs air or water, light can travel through the vacuum of space. So this property is what makes astronomy possible. Even from billions of light years away, photons travel across empty space to reach our telescopes. So imagine if light behaved like sound and needed air, space would be completely dark to us. So thankfully, photons don't need a medium. So the universe is full of information waiting to be decoded. Now this image shows William Herschel's experiment from 1800s. One of the most exciting experiments in history. So he passed sunlight through a prism to make a rainbow. Then placed thermometers in each color. Surprisingly, the thermometer just beyond the red line where nothing was visible got warmer. So he had discovered infrared, the first evidence that invisible light exists. And this experiment opened the door to exploring the universe in wavelengths we cannot see. So every photon is just like a messenger, carrying a piece of the story of its source. So by studying light, astronomers learn about composition, temperature, motion, and even the life cycle of stars and galaxies. Amazing, right? Now with this, we conclude the section 1 of chapter 6. Next, we will explore how telescopes and instruments actually collect this light and transform it into data that astronomers can analyze.